Hello viewers, welcome to add-on. So today we are going to solve this problem based on SF and BM diagram. As you can see, there is a beam A, B, C, D. Let us say this is point B, E, F, and there are supports at A and F. There is a UDL between C and D, and there are 2 point loads, 1 kilonewton, 4 kilonewton. So let us see how can we solve this problem. So as you know, there are 3 steps involved whenever we try to solve a shear force and bending moment diagram problem. So first will be to draw the LBD of the beam to get the support reactions. By applying a equilibrium condition, we will get the support reactions. The second step will be to find the shear forces at every point. And the third will be to find the bending moments at every point. So let us try to make the FBD of the following beam. What we have here is A, B, C. Let us just name that vertical force at A is FAY, and vertical force at at F is FFY. We have been given that there is a point load of 1 kilonewton at B, and there is a point load of 4 kilonewton at E. So as you know that whenever we solve these problems, we need to convert the uniformly distributed load into a single point load to make the FBD. So let's see how can we do that. We have a uniformly distributed load which can be also called as a rectangular load. Let us say the value of our load is some K, and the length of the beam is L. So whenever you have been given such load, what you can do is you can find the total shear force or the total normal force, let us say, to the beam by integrating the entire point forces. So let us say I have considered a small element here, and the force on that will be K dx. Let us say the length of it is dx. What you can do now is just integrate it to 0 to x, which is 0 to L, to the entire length of the beam to get the total force. So as we know that for a rectangular load, then the K will be constant. As you can see in our problem, it is 2 kilonewton per meter, which is a constant. So just take it out, and what you will left with is K into L, and the limits are 0 to L. So this is the total magnitude of this load, and it will be acting at the center of the beam. So center of the beam right now will be the L by 2 from any other sides. If you are being given like a triangular load, the same thing you can apply there. Whatever the K you have given is, the loading condition can vary. So whatever, let us say some f of x you are given, so just put that f of x here and direct it to 0 to L. You will get the total load and just apply it to the center of the figure. And in the triangular load, the center will be h by 3 from this side and 2h by 3 from this side, wherever the load is more. So you can use this technique to convert UDL or UVL, uniformly varying load, into a point load and assume that it is acting at the center of the figure. So let us apply this concept here. As you know that the total length is 2 meter, the UDL total length from the figure, and the total value of that is 2 kilonewton into 2, which will be 4. So let us just draw it like 4 from 1 meter, because the center will be falling at 1 meter. Every length here is 1. So let us just say that it is 1. Fine. This is our MBD now. What we can do after this is apply the equilibrium condition, which is summation f at 0, summation fy is 0, and summation of movement at any point is 0. So as you can see, there is no horizontal force here. Just neglect this condition because there is no horizontal force. So we have Fy, like FAY, all these forces are in the y direction or in the normal direction to the beam. So we need this condition and we will need this condition. If we apply Fy is equal to 0, then we have Fay plus Ffy, and all of this in the downward direction. So we'll just take it as negative, and the transferring to the other side, it will just become 4 plus 1, which will be equal to 9. So let us call this equation as equation number 1. For now, I have considered upward force as positive and downward as negative. You can change this, it won't affect your solution. So let us solve for that. Further, we have a moment at any point is 0. So assume that let us assume that we are calculating at A, because whenever we calculate movement at some point, if we calculate at the point where the unknown force is acting, the unknown forces will not be there in our equation. Why? Because what is movement? Movement is anything was forced into perpendicular distance. So this distance will become 0 if the point is going through if the force is going through that point. So that is why we will consider movement at A, because the Fay will disappear then. You can calculate it, the movement at any point in the given beam, and the answer won't change. For now, we'll just calculate at Fa. So what we have is 1 kilonewton force, and let us again establish a sign convention as clockwise as positive and anti-clockwise as negative. Again, you can change this, it won't affect your solution. You can reverse this. So the thing is, like 1 kilonewton into 1 will give you 1 only in the clockwise direction. So I have taken it as positive. And 4 into 3 we have plus 4 into 3, because again it is a clockwise direction. And we have 4 into 5 again in the clockwise direction. So 1, 2, 3, 4, 5 is the distance. Yeah, and for the 4 kilonewton force. And there is a negative because the movement because of this Ffy will be anti-clockwise. So that is why we are considering it negative. And the total length of the beam is 6, 2. Yeah, this is 6. So it will be 6 into Ffy. So you can just is equal to 0. Point at any point is 0. So you can just take it that side. So what will be 5 into 4 is 20 plus 12 is 32, 33. 33 by 6 will be Ffy, which gives you 5.5 kilonewton as Ffy. And just put this into our equation 1, you will get Fay value as 3.5. So as you can see, we have found out what are the reaction forces. So let us try to find shear forces now, which is our step 2. So shear forces in it is whenever you have a sudden like a point force here and here. So what you can do is you can calculate shear force before A and after A. It will give you a clear visualization of how the shear force is changing there. It might get confusing sometimes if you are trying to calculate at that point. So let us say at B, at C, at the UDL or the DE. Whenever there is a point load, a sudden point load, what you can do is you can try to calculate before and after that point. So I will just do that. I will calculate shear force after A. And the sign convention for this is so sign convention for this is whenever you are considering forces on the left side of the cross section, you need to calculate, you need to consider upward forces as positive and downwards as negative. And if you are considering forces on the right side of the beam, right side of the cross section, then just consider opposite of this. So downwards as positive and upwards as negative. So what we will be doing is we will be always considering on the left side of the beam, because it just makes our job easier. We do not need to confuse our sign convention. So you can just remember this condition and always try to calculate shear force from the left side forces of the cross section. So right now I have crossed the beam as after A. So let us say you are cutting the beam here. So what you can do is you can either calculate from the right side or from the left side. So what we will do is we will calculate always on the left side, because to not confuse us in the sign convention. So let us just calculate that. So we have Fay in the upward direction, which is positive because of our sign convention. So Fay value is 3.5. So we have 3.5 shear force in the upward direction, which is positive. So let us calculate shear force before B. So as I said, that whenever there is a sudden force, you can do calculate that before and after the point. It will make your job easy. So what we have before V is the same force as A because there is no force between A and B. So what we just write the same force, which is 3.5 kilonewton. If you cross-check the beam here, there is no force on the left except FA, which is in the upward direction, which is 3.5. If you now cross-check the beam right of the V, you need to consider this force also because there are two forces on the left now. So let us say I am calculating shear force after B or just right of B, whatever you prefer to say. We have 3.5 in the upward direction and -1 because it is in the downward direction. So we will take it as minus. So we have 2.5 kilonewton force. So let us say now we are calculating at C before C. So shear force before C. So before C we have forces such as A and V, which is acting at in the upward and in the downward, which means that there is no force between B and C. So the shear force which was at right of B will be at starting of C or left of C. So what I mean is, if you look at this section, like I am cross-sectioning it before C. So between after B and before C, there is no shear force. So the shear force will be same. It was the here, so which is 2.5, and after that there is a UDL. So there will be a linear variation, or the force will uh, gradually decrease because of that gradual decrease in this gradual downward force, which is 2 kilonewton per meter force. So it will gradually decrease up to D. So let us calculate shear force before D now. So before D, what we have is an entire force which is 4 kilonewton, and there was a 2.5 kilonewton force in the upward direction before C. So what we have here is in an upward force and a downward force of 4 kilonewton. So 2.5 in the upward and -4 in the downward. So we have -1.5 as our shear force at D. So let us calculate shear force at before E now. So before E. So before E, what we have is the same as D after D, which is, so there is no sudden force at D. So that's why we are calculating before D only, not after D. So it will be the same which what was before D. So before D also it will be the same because there is no shear force in between. So it will be -1.5. And after D, so let us try to calculate shear force after D. After E, what we have is we need to consider all the forces now. So we have a 4 kilonewton downward force, and what we had was -1.5 up till here, right, before E. So we need to add this right now because it is a downward force, so it will be negating. It comes out to -5.5. And let us calculate shear force at before E, F and at F. So before F we have -5.5 because there is no shear force in between, and shear force at F will become 0 because there is a sudden upward force which is positive. So +5.5 and the -5.5 before, so it will just become 0. So as you can see, we have calculated all the forces, but there is something like you need to consider before getting to the answer. So the thing is, like as you can see, there is 2.5 force positive in the direction in the like there is a positive 2.5 kilonewton force before C, and before D there is a negative force. So in between somewhere here before C and D, so between C and D the force must go to 0. The shear force must go to 0 to go it into negative direction. So we need to calculate that point also. Why do we need to calculate that? Because we know that shear force whenever it will become 0, so let us say shear force is 0, the bending moment will be maximum at that point. So we need to make the bending moment diagram also. So but it will be very useful if you find out the point where the shear force is 0, so that we know that certainly we know that at that point the bending moment will be maximum. So that is why we need to find where the shear force is going to 0. Let us try to calculate that point. So we have 2.5 kilonewton force, and it is gradually decreasing to -1.5 because of the UDL. So let us say we have 2.5 kilonewton force, and the value of UDL is 2 kilonewton. So let us say this is the UDL we have. And let us say at some x distance, if it is becoming 0, and then it is going to minus 1.5, let us say. At the starting, we had 2.5. So we just need to find out that x 2.5 minus 2 is the magnitude of the UDL, which is downward acting, into x is 0. So the x will come out to be 1.25. So what does it represent is after 1.25 meter from the UDL, the shear force will become 0, and after that it goes to the negative direction. So that is why we have found out using this technique. So where the shear force is 0, and then what we will do is we will make the bending moment maximum at this point, or we will find the bending moment at this point. So we can also prove that this condition. So why is there that shear force whenever is 0, the bending moment will be maximum? So the thing is, shear force will be dm by dx. So if you have any function like f of x and you want to make it maximum, what you will do is you just differentiate and equate it to 0. You will find out the point. What it means in calculus is that the slope of the function at that point is 0. So it can be either maximum or either minimum. You will find a double differential and equate it to, and if it is negative, you say that it is maximum, and if the double differential is positive, you say that it is minimum. So that is the basic concept in calculus. So we are just using this concept here. What we have is we need to find the maximum bending moment. So what we have is dm by dx. So let us say this is some function which we need to find the maximum of. So dm by dx we equate it to 0, which is shear force equal to 0. So that is why whenever the shear force is 0, the bending moment will be maximum or minimum. Whatever the value, if the value is in negative, we'll just say that it's in minimum, and if the value is in positive, we'll say that it is maximum. So let us move ahead and calculate our shear force diagram. What we have, let us not do it here. Yeah. So we have a beam. Let us just draw the point here. It's C, T, E, F. At A, we have a vertical force of 3.5 kN MS. Yeah. And as you can see, we have calculated all the shear forces. So before B is 3.5 and after B is 2.5. So before B it is 3.5 and after B it is 2.5. So let us say this is 2.5 something. Before C it is 2.5 and before it is minus 1.5. So before C it is 2.5 and after it is, after like D it is a minus 1.5 there. So it will vary linearly. Before it is minus 1.5 only, and after it is minus 5.5. So before it is minus 1.5 and after it is minus 5.5. Until F it is same, and at F it will become 0 because of that upward force. So this becomes our shear force diagram. Let us now calculate bending moments at every point. So you can just calculate bending moment at the solid point and not before and after. So this helps and this shortens up the solution, because the thing is like the force at that point will not affect the bending moment. So you can just calculate at the point. So let us say I am calculating at A. I know that A and F, the bending moment at A and F will become 0 because we need to consider the entire beam. So let us say I am calculating at A, then I need to consider all the forces on the right or on the left. So that will become 0 because of the equilibrium condition which we had. So again at F it will become 0. So the sign convention here is whenever you are considering force on the left, your just has to give clockwise as positive and anti-clockwise as negative. And the reverse is true if you are considering forces on the right side. So anti-clockwise is positive and clockwise is negative. So the thing is like in the bending moment, we will consider the forces on the right side sometimes. Let us say I am calculating at E. So and either I can consider forces on the left or on the right. So there is only one force on the right? So it will be very easy for me to calculate on the right only. So sometimes it will be easy for you to calculate on the right also. So you need to like take into consideration both the conditions whenever you are considering on the left or on the right of the cross section which you have made, or at the point which you are calculating. So let us say I am calculating at B now. So bending moment at B. So bending moment at B will be either I can take all the forces or I can just take the A force. So I will do that because it is easy for me. So 3.5 into 1, which will become 3.5, and it is in the clockwise direction and it was in the left side. So it will be positive 3.5. Let's say now I am calculating at C. So there will be two forces at A and at minus 1 at B. So just multiply the force which is at A into perpendicular distance. So it is 2 minus, because it is a clockwise, so it is a positive, and minus 1 kilonewton force into 1 is the perpendicular distance of that 1 kilonewton force, and it is in the anti-clockwise direction, so it will be negative. So let us just calculate that. 3.5 into 2 will be 7 minus 1 is 6. So at C we have 6 kilonewton meter of a bending moment. So let us calculate at the point where we like there is a point, let us say called it as X, where we said that shear force is 0 and bending moment will be maximum. So we need to calculate at that point also. So how can we calculate that at that point? So let us just draw our beam. We have A, B, C, D, E, F, and we have UDL here somewhere. And at 1.25 distance, the shear force is going to 0. So we need to consider forces either on the left or on the right. So for now, we'll just consider on the left because we have been doing that before, and it will be better for us, easy for us. So we have 2 kilonewton force into 1.25 is the distance. So the shear force will become 2.5. Yeah, 2.5 for the UDL. And at B we have 1 kilometer downward, and at A we have 3.5 upwards. The distance is, as you can see, here is 1 and here is 1. So you can just calculate the bending moments at that point where the shear force is 0. It is coordinated X. So you have 3.5 into 1 plus 1 plus 1.25. That will give you 3.25. Yeah, that will give you 3.25. And then you have a minus 1 force. So 1.25 and 1 is 2.25 into 1. So 2.25 into 1 in the negative direction, because the distance is 2.25 and the force is 1, and it is in the anti-clockwise direction. So that is why we have taken it as negative. And also we have a force of 2.5 acting at this is, yeah, this will not be here. So the force will be acting at the midpoint of this. So the so the force will be 1.25. The entire force will be acting at the midpoint, which is 1.25 by 2. So it will give 0.75. 1.45 by 2 will 0.625, sorry. So yeah, you need to calculate at that point. So we have an anti-clockwise moment of, the force will be 2.5. The force will be 1.25 into 2, which is 2.5, into 0.625. So the moment comes out to be like 3.5. You can do it in your calculator. 2.25 times 3.5. Yeah, the moment comes 7.5625. After that, we can calculate at point D. Let us consider the right forces now, because there is a lot of forces and you need to consider when you consider on the left. So On the right, we have an anti-clockwise movement of F into 2, which will be positive because on the right it is now, and it will be 4 into 1 on the clockwise direction, so it is a negative. So F is 5.5, as we know, we are going to calculate that. It will be 11 minus 4, which is 7. So at F we have a 0. Sorry, at E also we need to calculate. So at E we have F into 1, which is 5.5 in the positive because it is and the anti-clockwise. At F we have 0. So let us now make the bending moment diagram, as we have bending moment as every point. So let us say this is A, B, C, D, E, F. So at A you have a 0 bending moment, as you can see here. At B you have 3.5. At C you have 6. So 0, 3.5, let us say this is 6. At X you have 7.5625. So let us say somewhere here, which is 1.25 from C, you have 7.5625. And at D we have 7. D, let us say you have 7. E you have 5.5. Let's say here is 5.5, and F you have 0. So as you know, whenever you try to join this, you have to join linear wherever the shear force was constantly varying. And whenever there was a UDL, you need to make a parabola out of it. And let's just join here and then say here. So this will be your bending moment diagram. So that will just quickly explain why we have drawn a parabola and a linear line here. So again, it goes back to shear forces dm by dx. So whenever your shear force is varying constantly, it was the case between AB and CD, but it was linearly varying between C and D because of the UDL. So let us just see it is a, let us say shear force is some constant C. So what you can do is you can just integrate this and you can get like Cx plus D something. The bending moment will vary linearly whenever the shear force is constant. And whenever, let us say this is some Cx, which is a linearly inclined line. So you can just again integrate it. You can get Cx squared plus something D, which is parabolically varying whenever the shear force is varying linearly. So that is why we have made a parabola wherever the shear force is linear, and a linear line whenever the shear force is constant. So yeah, that solves our problem, as we